So we move on now to the topic of implicit differentiation. And so the purpose of this video and this process is to be able to find dy dx, to be able to find the slope of the tangent line, even if we don't have an explicitly defined function. So even if we don't have y equals x squared, where we could just say, hey, cool, dy dx is 2x, even if we don't have an explicitly defined function like this, we want to be able to find dy dx. We want to be able to find the slope of the tangent line, even if we're dealing with something like the equation of a circle. So before I really get into the details of how to do this, I do have sort of two, I guess I call them review questions about derivatives. And those two questions are these. What is the derivative of x with respect to x? And what is the derivative of y with respect to x? Right? And if you want, pause the video for a minute, try to think through these, because I think there's definitely some thinking to happen. But the first question, what is the derivative of x with respect to x? Notationally, that would be dx dx. Just like the second question, the derivative of y with respect to x is dy dx. But remember, derivative is also about rate of change, right? This question here is saying, what is the rate of change of x with respect to x? In other words, whenever x changes by a certain amount, how much does x change by? And the reality is, that's silly. The derivative of x with respect to x is 1. Like as x changes, right? In the second one, when I say what's the derivative of y with respect to x, this is kind of unknown. I don't know what y is. I don't, like in this problem right here, I don't have any sense of the relationship between x and y. So when I think, hey, what's the derivative of y? I can't respond with, oh, it's x squared, or oh, it's 5, or oh, it's 1. I just have to say, the derivative of y with respect to x is this. This notation is reserved for the concept of the rate of change of y with respect to x. How much y is changing when x changes by a certain amount. And these two things are going to be really important for us as we move into the next section to prepare for implicit differentiation. So in this next section, I'm going to ask us to take the derivative of several different functions, right? So the first one I have here is asking, hey, what's the derivative of the sine of x squared? And the answer should be, that this derivative is the cosine of x squared, but because there's something inside of here, there's a function composed within there, I have to multiply by the derivative of that, which means I will multiply by 2x. And so I'm not going to take the time to clean this up, but this would be 2x times the cosine of x squared. If I were to ask another one, what is the derivative of the sine of the square root of x? Okay. Well, this is very, very similar. This will be the cosine of the square root of x times, well, because there was something inside here that was other than x, other than the independent variable right here, I have to multiply by the derivative of that thing, which is 1 over 2 root x. Again, I'm not going to worry too much about simplifying that thing. I just want us to see a pattern. One more boring one. What about the derivative of the sine of, what the heck, the sine of the cosine of x, right? Well, this would be the cosine of, we leave the inner composed function alone, cosine x, times the derivative of what was inside. That thing that was inside was cosine x. The derivative of the thing that was inside was negative sine x. And again, we could pretty this up, but I'm just getting across the idea. We know how to do the chain rule. You guys have seen this before. So this sort of begs an interesting question. Why don't we use the chain rule when we have something like the sine of x? And I would argue that if you want, we can use the chain rule, right? We would say this is the cosine of, leave the inside alone, and then multiply by the derivative of what's inside. But what is the derivative of x with respect to x? The derivative of x with respect to x is 1, which means my whole answer here ends up just being cosine x. All along, we've sort of, I guess we could say we've been doing the chain rule. It just wasn't necessary because the thing inside was x. The next question is where we get to something real, right? Something that's really different. What's the derivative with respect to x of the sine of y? Right? Well, according to the past problems we've done, there's a pattern here. We take the derivative of the outer function, which is cosine. We leave the inside alone. Then we multiply by the derivative of the component of the thing that was composed inside, right? Well, what's the derivative of y? Up here, I knew the derivative of cosine was negative sine x. Up above that, I knew the derivative of x squared was 2x. Down here, what's the derivative of y? We may not know explicitly, but we can write it, and that was what the previous slide in this video was about. The derivative of y is dy dx. So the short of it is, whenever you are taking the derivative of something that involves a variable that is not the independent variable right here, we effectively have to do the chain rule, because the thing that's inside there is not just x. Its rate of change is not 1 like it is up here. We have to multiply by the derivative of that thing. And so that means, just as one more little example, even if someone were to ask you what's the derivative of y squared, if they said what's the derivative with respect to x, we have to treat this like a chain rule. The outer function here is the squared function. The derivative of this thing will be 2 times leave the inside alone, which is y, and then we will multiply by the derivative of what's inside, that's dy dx. These concepts right here, the business of multiplying by the derivative of that y function that's inside, that's the entire key to implicit differentiation. So I have an example here for us. I want us to find dy dx given the relation x squared minus 2y cubed equals 5x. Notice here that when you look at what they're asking for the derivative of, the independent variable is x. That means x is the thing that doesn't require the chain rule. Everything else will require the chain rule. Right? So for this derivative, my x squared, that derivative is 2x. Then minus, for my 2y cubed, that derivative is going to be minus 6y squared. But because it's a y, I need to multiply by dy dx. That's sort of the chain rule coming into play. And then for the last part, equals the derivative of 5x is just 5. I don't need a dx because it's being done with respect to x, right? So now that I have this thing, they want me to find dy dx. So I now need to solve this for dy dx, right? So if I subtract that 2x over, I'll have negative 6y squared dy dx equals 5 minus 2x. We'll divide the negative 6y squared over. That gives me dy dx is 5, that looks like a negative, equals 5 minus 2x over negative 6y squared. And that's the derivative. That's dy dx. Now, this might be a little bit strange to you. Up to this point, our derivatives have only ever depended on x. If we ever needed to find the slope of the tangent line, this dy dx thing, we just plugged in x. In this case, we may very well need to evaluate this using both x and y coordinates of a point. So we'll see that come up in a little bit. Another example, find dy dx given this relation. This one's a little bit more complicated. In fact, I'd like you guys pause the video for 10 seconds and think about what's going to make this derivative a little bit more complicated. So think about that for 10 seconds, then come back and we'll talk about it. In my mind, one of the more complicating elements is that this right here is going to require the product rule. That's x squared times y. There are two things there. So what I'd like you guys to do now is try pausing the video and taking this derivative on your own, just one step of it, and see if you've got the same thing as I do. So first, this product rule right here. I do the derivative of the first thing, that's 2x, and I leave the y alone. Note that I do not need dy dx here because I left the y alone. But right here, I'm going to leave the x squared alone. And now, when I do the derivative of y, that derivative of y, I mean, if we just think about it, the derivative of y is dy dx. Okay? Then we'll have minus, the derivative of sine is cosine, so this is the cosine of y. Again, times dy dx, because there was a y that was composed inside of that. And finally, this thing is equal to 15x squared. Now, I need to find dy dx, and there are two of them, and this happens fairly commonly. When there are two of them, what we need to do is we need to factor them out. Right? But I can only factor them out if all of my terms have that. This term doesn't have a dy dx in it, so I'm going to move that term over, and that will allow me to factor the dy dx out of both of these. Right? So I have x squared dy dx minus cosine y dy dx equals 15x squared minus 2xy. Then at this point, because both terms have a dy dx in them, I can factor that dy dx out. So we factor dy dx, leaves me with x squared minus cosine y, still equals 15x squared minus 2xy. And now the last thing I have to do is take this and divide it to the other side. We finally end up with dy dx equals 15x squared minus 2xy all over x squared minus cosine y. I'm not about to say that this is the prettiest derivative ever, but we did it. Like, this is one of those, like, hey, we got an expression for what the slope of the tangent line is going to be. If I had a point, I could evaluate this expression using the x and y coordinates of that point, and I could find the slope of the tangent line. From there, I could even find the equation of the tangent line. So in this last example, and I want to try and do it quickly, I want to try and pull all these things together. Right? We just, like 10 seconds ago, talked about the fact that we can get an equation of a tangent line if only we can find dy dx. In fact, this problem is going to be nice because I'm already giving you a point. So the first step here is to find dy dx. So I'd like you to pause the video, try to find dy dx on your own, and then just sort of check your work with me. So to find dy dx, I take the derivative of this with respect to x. Right? So the derivative of x is going to be 1. On the other side, I got to be careful here. My outer function is my cubed function. In order to take that derivative, I bring the 3 down, I leave the inside alone, that's my 2 minus y squared, and I drop my power to a squared. Now I'm supposed to multiply by the derivative of this thing. But that thing inside has a y in it, right? I mean, the derivative of that thing is going to be negative 2y times dy dx. When I take the derivative of that thing that has a y in it, I get that dy dx. Right? So now I could pretty this up a little bit. 1 equals, I'll put these 3 and the negative 2 together, negative 6y times 2 minus y squared squared times dy dx. And now if I really want to find dy dx, if I want to find the slope so that I can find the equation of the tangent line, I'm going to need to get this, I'm going to have to isolate this dy dx. So I'll divide all this over. I'm going to end up with dy dx being 1 over negative 6y times 2 minus y squared squared. Now the last thing I have to do is I evaluate using this point. And you guys may remember an assignment like a week or two ago where you were upset because there were problems where I asked you to evaluate using a point. And you were like, man, why is there a y coordinate if we only use the x? Well, now your complaint is the opposite. This expression only has y's in it, so I'm actually only going to use y equals 2. To find my slope, I'm going to have 1 over negative 6 times 2 times 2 minus 4 squared. So this is 1 over negative 12 times 4, so negative 1 over 48. This is my slope. So now that I have that, I can combine it together with the point, which was 8 comma 2, and I'll get y minus 2 equals negative 1/48 x minus 8. Sorry this video ran a little bit long, but I hope that all makes sense, and I hope you guys get a chance to really get these.